Okay. So section 8.4 is on adding, subtracting, multiplying radical expressions. Whenever you see that word radical, just think of roots. You can think of square roots. You can think of cubic roots. You can think of quartic roots. Any root with an index of n where n represents a positive integer. So what are our learning objectives for this section? We, once again, are going to be able to learn how to add, subtract, and multiply radical expressions. And then lastly, we'll be able to use polynomial multiplication to multiply radical expressions. So same exact concept, but from a function perspective. Let's start off with some warm-up problems. That first warm-up problem, we're asked to add these two subtract these two polynomials from one another. And because that second polynomial has parentheses around it, we really need to utilize our knowledge of distributive property, distributing that negative to each term inside those parentheses. So when we do that, we can rewrite everything out. Our 3x squared plus 9x minus 5 stays the same. When we distribute that negative, now we're looking at negative x squared plus 2x, because a negative times a negative is a positive, and then minus 3. That, I would say, is the most challenging step when it comes to this sort of problem. Now, this next step, all we're doing is we're color coding so that we can combine some like terms with one another. We have our second degree term. We have our first degree term in green, and then we have our constants in blue. So 3x squared minus x squared gives us what? 2x squared, right? Because x squared is just 1. X squared and 3 minus 1 is 2. Then we have 9x plus 2x gives us 11x. And then last but not least, we have a negative 5 minus 3 gives you negative 8. You guys are tired today. Did you enjoy your spring break at least? Got a little bit of rest? Yeah. Anyone like go to the beach or relax? I was dreaming about the beach. But I'm excited for summer. You just got to push through. You guys have literally like 3 to 4 weeks left, and then you're good. All right. Our second warm-up problem, there's 2 parts to it. We have a part A and a part B. That part A is just reviewing your knowledge of foiling. So it's the fancy distributive property, our whole first, outer, inner, last. So we have 2 times 4, which gives you 8. Then 2 times negative a gives you negative 2a. Then a times 4 gives you a positive a4, also known as positive 4a. And then a times negative a gives you a minus a squared. And then let's combine some like terms. Those middle terms we can add together. Negative 2a plus 4a just gives you a positive 2a. And then let's put it into descending order. So we're going to bring that negative a squared to the front. And then we'll move that constant to the back. So your final result in expanded form is negative a squared plus 2a plus 8. And we're done. Let's go ahead and look at part B now, which is another FOIL, but it's just to remind you guys that if you have a binomial and you square it, you're not squaring this and having that be your answer. You need to think FOIL. The best way to do that is just write, that exponent tells us how many times we are writing out that binomial and then multiplying by one another. Once it's in this sort of expanded form, then we can utilize our fancy distributive property to really FOIL everything out. You'll notice we have a special factoring property here because they're all just 9 minus 5y times 9 minus 5y. So those inner terms are going to be exactly the same. They're going to be negative 45y. And then that last term is just negative 5y times negative 5y, which is positive 25y squared. Once again, combine those middle terms and put it into descending order. So we're going to have 25y squared first, then a minus 90y, and then a plus 81. And we're done. And let's see, Ryan, do you think you can close the door for me? Thank you so much. Any questions at all on these warm-up problems? Yeah.
And then we get obviously the number. So because they were both negatives, like the 35y in a sense, and you have factors in a sense, they add up in a sense, right?
Yeah, exactly. They're both negative values. So when you are adding, you can also just put a little plus here and add these two negatives. So just add the values themselves and then stick the negative in the front, and then you got it. So 45 plus 45 is 90, but they're both negative, so stick the negative in the front, and so we get negative 90. Anytime you're adding two negative numbers together, anytime you have a negative number and you're subtracting a value, it's always going to be add the numbers up and stick the negative in front. Yeah. All right, so let's jump into our first objective for today. We have a little notes section on adding and subtracting our radical expressions. Maybe I'll have a student read this. Herlinda, do you think you can read this for me? Radicand, yeah.
It's just like radicals with the same elements and the same radicals to remind us they were the same as like terms.
Beautiful, thank you. And this is just the more formalized definition of what like radicals stand for. It's literally just dealing with roots that have the same index. And so similar to like terms, 5x plus 10x, like radicands are like the square root of 5x plus the square root of 5x. And so we'll go through concrete examples together, but the biggest thing that I think we'll find to be most helpful is treat that radicand as like a variable itself. So let's say you were adding, for example, 3 square root of 5x plus 10 square root of 5x. Off to the side, just say, okay, well, the square root of 5x is w. So we're really looking at just 3w plus 10w, and we know what that is. What's 3w plus 10w? Yeah, it's 13w. And now we can substitute back in that square root of 5x. So our final result is just 13 times the square root of 5x. So when you treat that radicand as a variable, it makes it a little less overwhelming. But we'll practice a few examples on this page together to really enforce that material. So our example 1, we're looking at 2 square root of 2 minus 7 square root of 2. Again, treat that square root of 2 as a variable. Let's call it w. We're going to let W be equal to the square root of 2. And when we do that, we're really essentially just looking at 2W minus 7W. What's 2W minus 7W? Negative 5W. And then finally, let's substitute in that square root of 2. So what's our final answer? Negative 5. What's W equal to? Yeah, square root of 2. There we have it. We're done. Try another example together. We have 5 cube root of y plus 4 cube root of y. Again, this cube root of y, we're going to have that just be a variable. Our most famous variable is x. So why don't we just let the cube root of y be equal to x? Meaning wherever you see that blue highlighted, we are just going to put in an x. 5x plus 4x. What's 5x plus 4x? 9x. And now let's replace it back in with what we substituted. So what's our final result? 9 cube root of y. And we're done. Do one more example together. We have 7, the fourth root of x minus 2, the fourth root of y. The fourth root of x and the fourth root of y, are those like radicands? Okay, are they kind of like terms? How many people say yes? How many people say no? It's not, right? One's yellow, one's orange. Those are different colors. X and Y, different variables. So can this be simplified? Cannot be simplified further. Done. Any questions at all on this slide? Right. So we will continue to trek along then. Let's look at another few examples together. Now that we're getting the hang of this whole variable thing, we'll add some more terms. So this time I'm not going to write out the substitution, but I'll still color code it so you can visually see what is acting as that variable x, for example. Two x minus 6x plus 4x. Well, what's 2 minus 6? Negative 4. And what's negative 4 plus 4? 0. So what's our final result? 0 times the square root of 5n, which is just 0 times anything is 0. We're done. Look at part B. We have the fourth root of 3xy plus 5, the fourth root of 3xy minus 4, the fourth root of 3xy. So what's our variable here? Our whole fourth root of 3xy. That way we're just going to look at our coefficients to simplify from there. The coefficient of that first term is just 1. What's 1 plus 5? 6. And what's 6 minus 4? 2. I think someone's like music is playing. You just make sure you turn it off. It's been playing the entire time. Could be a little annoying. Okay. All right. So our final result is 2/4 root of 3xy. And we're done. Any questions at all on this page? Let's do another example together. So now we're looking at the square root of 20 plus 3, the square root of 5. So now what we're trying to do is we're trying to bring in our knowledge of simplifying roots and then combining like terms, aka our like radicals with one another. So let me just write the problems out for each part, and then we'll tackle each one bit by bit. Bless you. It's fine. I have a friend too. Once they sneeze once, it's like they can't stop. And we were in college together and he was in one of my classes, started sneezing. I kid you not, like he must have sneezed like for 20 minutes straight. And it got to the point where like the professor was like, you can go home. Like we can't get anything done if you're sneezing the whole time. All right, part A. Which one are we able to simplify using our knowledge of simplifying radicals? First one, right? Anytime we're simplifying radicals, especially square roots specifically, we want to think, what's the highest perfect square that can go into 20? You don't technically have to do the highest. If you do the highest, then you just have less steps. But what's any perfect square that goes into 20? What times what gives you 20? Think of factor pairs. Yeah, nice job, Sahid. We have 4. So the square root of 4 times what gives you 20? Times the square root of 5. And we know the square root of 4 is just 2. So in simplified radical form, the square root of 20 is just 2 times the square root of 5. Now that's really helpful because now when we add 3 square root of 5 to that, we have like radicals. And so what is 2 square root of 5 plus 3 square root of 5? 2 plus 3 gives you 5, and then the like radical is that square root of 5. So our final result is just 5 square root of 5. We're done. Okay. Now let's look at part B. We're no longer in square roots, we're now in cubic roots. So we want to think, okay, what times what gives you that number? Let's first look at 24. And the easiest way to go through whether it's cubic root, quartic root, the index being 5, 6, 7, start with the lowest number. Don't start with 1. 1 doesn't help us here. Always start with 2. 2 times 2 times 2 gives you what? What's 2 to the third power? 2 times 2 is 4. What's 4 times 2? 8. So 2 to the third is 8. Is 8 a factor of 24? It is. So we can break up this cube root of 24 into the cube root of 8 times what? 8 times what gives you 24? 3 times the cube root of 3. Okay. Now let's look at this second one, 375. That's a large number. But once again, let's start off small. So 2. 2 times 2 times 2 gives you 8. Does 375 go into 8? I actually don't know that at the top of my head. I know what the number is, but I'm trying to work through this problem with you guys. So 8 goes into 37 4 times. And then 8 goes into 55 6 times, right? And then we have 7 left over. So doesn't go in. Needs to go in perfectly. Right, let's move up then. 3 to the third. 3 times 3 is 9, times 3 is 27. Does 27 go into 375? I doubt it does. Just doesn't look like it does. 27 goes into 37 one time. Then we have 10. We're going to bring down that 5. 27 goes into 105 like 4 times, right? That gives you, oh, not even, right? 20, 40, 60, 80. No, it should. 20, 40, 60, 80, 100, 101. But it doesn't go in perfectly. So 3 doesn't work. Next number up, 4 to the third. 4 times 4 is 16, times 4 is 64. Does 64 go into 375? And we can just do that by simple multiplication. 64 times 2 gives you 128. And then 128 doubled gives you 256. And then if you add another 128 to 256, you end up going over, right? Get 3, or you're just below it, 374. So you know that 64 doesn't go in. Finally, what do we arrive at? 5 to the third. 5 times 5 is 25, times 5 is 125. Ooh, does 125 go into 375? Yeah, goes in how many times? 3 times. Would you look at that? That's going to be our like radicand between the two. So when we rewrite this, I'll put this maybe below here. We can rewrite this as the cube root of, we have cube root of 3 times the cube root of 125. This over, more space. Times the cube root of, does everyone see that? sort of went through this problem a little on the slower end, but I really wanted you guys to absorb the step-by-step procedure. If you were able to very easily identify, oh, 5 cubed 125, that very easily goes into 375, then yeah, do that. Jump straight up to that. But if you weren't able to realize that, all you went through was 2 to the third, 3 to the third, 4 to the third before you got to your final result of 5 to the third. Now let's simplify this. The cube root of 8 gives you 2. Yeah, nice job, Chris. And what's the cube root of 125? It's just 5, right? 5 times 5 times 5 gives you 125. So now when we combine our like terms or our like radicands, what's our final result? Negative 2 minus 5 is? 2 minus 5 is negative 3, right? Times the cube root of 3. And we're done. Does everyone see that? So let's continue. Let's look at part C. Now we're looking at quartic root. So what times what times what times what? And so the first one you want to think about is the easiest number, 2. 2 to the 4th power gives you what? What's 8 times 2? 16. Does 16 go into 48? How many times does 16 go into 48? Not twice, but 3 times. Let's keep that 1/2 in the front. And so this 4th root of 48 is just broken up into the 4th root of 16 times the 4th root of 3, because 16 times 3 is 48. And now this second part, we have 243. Does 16 go into 243? Don't think it does. But what number do you know for a fact goes into 243? Kind of look at what we have, that second orange one. Put it into my calculator. Can't think today. That second orange one is 3, right? So 3 goes into 243 how many times? 81 times. And are we able to take the 4th root of 81? Well, 2 to the 4th is 16. What's 3 to the 4th? If 3 to the 3rd is 27, what's 27 times 3? 81. So the 4th root of 243 is the same as the 4th root of 81 times the 4th root of 3. Now let's just simplify. This is the hardest step. Once you get here, it's all downhill. 4th root of 16 is 2. That 4th root of 3 is going to be that like radicand between these two terms. 4th root of 81 is 3. Once again, we have that 4th root of 3 is our like radicand. We can simplify these products. 1/2 times 2 is just 1. So we end up getting just the 4th root of 3 for that first term. And then 2/3 times 3, the 3's cancel out. So we're looking at a -2 4th root of 3. So what's our final result? What's the 4th root of 3 minus 2, the 4th root of 3? It's just negative 1. the fourth root of 3. Or you can just say negative the fourth root of 3. And we're done. Any questions on this part? It's tedious, but if you understand the steps, it's actually not too terrible. Right. Let's move on to our second objective, which I personally think is a little bit easier, dealing with just multiplying radical expressions. And we have our general definition of our product property of roots, which we've covered in previous sections, but it's just to reiterate and remind you. And then also now looking at it from the perspective of combining like radicals. So as stated in this paragraph, we've already used our product property to simplify, but we can also use it in reverse to multiply. So we're now looking at the reverse engineering aspect of multiplying roots that have expressions, aka multiplying radical expressions. Okay, so example 4. Let's look at these two concrete examples. Our part A, we have 6 square root of 2 times 3 square root of 10. So the easiest thing I would say to do is multiply the coefficients, get that product, and then multiply the roots, and then simplify the root if you can. So 6 times 3 gives you 18, and 2 times 10 gives you 20. So your answer is 18 square root of 20. However, you can simplify that square root of 20 into square root of 4 times square root of 5. And we know that the square root of 4 is 2. So we essentially get 18 times 2 times the square root of 5, which leads us to our final results to be 36 square root of 5. And we're done. Part B, once again, deal with the coefficients first, and then look at our roots. So we have -5 times -4 is a positive 20. And then we have the cube root of 4 and the cube root of 6. Well, 4 times 6 gives you 24. So we're looking at the cube root of 24. That's your answer, but you want to simplify more. That cube root of 24 can be broken up into the cube root of 8. And 8 goes into 24 3 times. Just like that previous example we worked on together. Now that cube root of 8, what times what gives you 8? 2, good. So we're looking at 20 times 2 times the cube root of 3. Last but not least, let's combine 20 and 2 to get 40. So our final result is just 40 times the cube root of 3. And we're done. Any questions? Okay. Let's do some more examples together. Multiply the coefficients. Again, please make sure you turn off that music. It's very frustrating, especially because I can hear it. I can't even imagine like the people sitting next to you, how annoying that must be. It's not cool. If I have to ask again, I'll just have you leave the classroom. Okay. 10 times 4 gives you 40. And then we have the square root of 6p to the third times the square root of 3p. That's just the square root of 18p to the what? What's p to the third times p? Properties of exponents. What's 3 plus 1? 4. Yeah, p to the 3 times p is just p to the fourth. And now, what can we break this up into? Well, let's look at them separately. This is the same as the square root of 18 times the square root of p to the fourth. Perfect square that goes into 18 is 9, so we can break that up into square root of 9, square root of 2. And the square root of p to the fourth, that's a perfect square. That's just p to the second. Let's go ahead and bring down that 40. Don't want to forget about that. So now we're looking at that square root of 9, which is just 3. So we have 40 times 3. I'm going to bring that p squared to the front as well. And then last but not least, we have that square root of 2. 40 times 3 gives you 120. So your final result, 120 p squared times the square root of 2. If you wanted to write it as 120 square root of 2 times p squared, either of these I would accept. And do done. Go ahead and look at B. So once again, product of the coefficients, and then product of these roots, and then simplify. 2 times 3 is 6. Quartic root of 20y squared times quartic root of 28y cubed. Well, 20 times 28 gives you, let's see, 10 times 28 is 280. Double that and you get 560. So 20 times 28 is 560. And then we have y to the second times y to the third is y to the fifth. And now let's simplify what's underneath the root here. So we're taking the quartic root. 2 to the fourth is 16. Does 16 go into 560? Good. Let's see. It goes in 35 times. So we can break this up into the quartic root of 16 times the quartic root of 35, and then times the quartic root of y to the fifth, which can be broken up a little further, but we'll hold on that until the next row. Quartic root of 16 is 2, so we have 6 times 2. And then we have this quartic root of 35, which can't be simplified further. And then the quartic root of y to the fifth is the same as just the quartic root of y to the fourth times the quartic root of y. And we know that the quartic root of y to the fourth is just y. So, and then 6 times 2 is 12. Trying to keep everything color-coded so you could see what's going on. So our final result is 12 times the quartic root of 35 times y times the quartic root of y. And we're done. This is in fully simplified form. Any questions at all? Let's keep going then to our final objective for today, where we'll be using polynomial multiplication to multiply radical expressions. So in this section, we're once again using our famous distributive property and dealing with foiling out, especially when we're multiplying two binomials by one another. And then if you're taking, like, for example, the square root of 5 times the square root of 5, what does that just simplify to? What's the number inside? It's just 5, right? Because the square root of 5 times the square root of 5 is the same as the square root of 25. But what's the square root of 25? 5. So be on the lookout for those types of simplifications. So in example 6, we have two parts. Square root of 6 times square root of 2 is the square root of 12. And square root of 6 times the square root of 18 is the same as, okay, well, 6 times 10 is 60, and 6 times 8 is 48. So 60 plus 48 gives you 108, so the square root of 108. And now let's simplify these radicals. Square root of 12, what's a perfect square that goes into that? 4. Can break that up into the square root of 4 and square root of 3. And then what's a perfect square that goes into 108? We know 4 goes in, but there might be another perfect square that goes in. Because 4 goes in, half of 108 is 54, and then half of 54 is 27. So, and 27 can be broken up into 9 and 3. So 36 also went into 108. We have 9, 3. 36 goes into 108 3 times. All right. But now let's simplify. We can simplify square root of 4. And we can simplify that square root of 9. Square root of 4 is 2. So we're looking at 2 square root of 3 plus square root of 4 is 2. Square root of 9 is 3. And then we have the square root of 3. 2 times 3 gives you 6. So we're looking at 2 square root of 3 plus 6 square root of 3. Like radicands, 2 plus 6 is 8. So our final result is 8 square root of 3. And we're done. Look at part B, where we're multiplying cube roots. The cube root of 9 times 5, well, that's the same as 5 times the cube root of 9. Put that coefficient in the front. And then we have the cube root of 9 times the cube root of 18. Well, we have 9 times 10 is 90, and 9 times 8 is 72. 90 plus 72 is 162. So we have minus the cube root of 162. And then let's simplify this further. So the cube root of 9 can't be simplified any further, which means there's a good chance that this is going to be the like radicand between these two different terms. So let's ask ourselves, does 9 go into 162? And it does. How many times does 9 go into 162? Bless you. It goes into 16 once. And then we have 72. And then 9 goes into 72 8 times. So it goes into 62 18 times, which could figure it out because we just multiplied the two together. So we can rewrite this. Should have just kept it as the cube root of 18 times the cube root of 9. And then we have 5, the cube root of 9. Now, cube root of 18, I don't think that I'd simplify that further. I want to make sure that you can't simplify. We have 2 to the third is 8. Does 8 go into 162? No. 3 to the third is 27. Ooh. Yes. Okay. So this problem actually isn't going to have like radicands. What we should do, once you go to that 162, just go up the way that we learned in the past few examples. You know, 2 is your base number. 2 to the third, 8. 8 doesn't go into 162. Okay, let's try out 3. 3 to the third, 27. How many times does 27 go into 162? Goes in 6 times. So you can rewrite this as the cube root of 27 times the cube root of 6. And the cube root of 27 is 3. So we get 5 cube root of 9 minus 3 cube root of 6. This is your final answer. Cube root of 9 and cube root of 6, there are no like radicands, so you just keep it as is. Yeah, so this part to the side, we can just cross that out. All right, any questions at all on this slide? So let's look at example 7. Utilizing FOIL now. 3 times 4 gives you 12. 3 times negative 2 square root of 7 is a negative 6 square root of 7. Negative 2 square root of 7 times 4 is a negative 8 square root of 7. Ooh, we have some middle-like terms. And then we have negative 2 square root of 7 times negative 2 square root of 7 is a positive 4. Square root of 7 times square root of 7 is just 7, right? Square root of 49, which gives you 7. So that 4 times 7 at the end is just 28. Those middle orange terms turn to a negative 14 square root of 7. And that beginning term, we have 12. Are we done, or can we combine some more like terms? Yeah, 12 plus 28 gives you. Yeah, so our final result is 40 minus 14 square root of 7. And we're done. Look at part B, where we're dealing with now some cube roots. Cube root of x times cube root of x gives you good old x. Cube root of x times 4 gives you 4 cube root of x. Negative 2 times cube root of x gives you a negative 2 cube root of x. And then negative 2 times 4 gives you a minus 8. Those middle two terms are like terms. So those can be combined to be what? 2 cube root of x. Our final result is just x plus 2 cube root of x minus 8. And we're done. A few more examples. This is just a notes slide, reviewing your knowledge of your special products, dealing with your binomial squares, a plus b in parentheses squared and a minus b in parentheses squared, what that factors out to be, and then also your product of your conjugates, how those middle two terms end up canceling out when you have the product of a plus b and a minus b. So the same thing holds true when we're dealing with radicals inside these binomials. We'll really get to see it in this example together. Right? These binomial squares, yes, you can expand it out and do the foiling, but that takes up time. So if you know your rules, just know that when they're both positive, those middle two terms are being doubled. So 2 times 2 gives you 4. Your middle two terms is 2 square root of 3 doubled, so that's your 4 square root of 3. And then the square root of 3 times the square root of 3 is just 3. So you get to this step in about 5 seconds, and then your last bit is you combine those constants. So your final result is just 7 plus 4 square root of 3. And we're done. From the difference perspective, now those middle two terms, you're adding it, but then you're sticking a negative in front. So 4 squared gives you 16. We have 4 times negative 2 square root of 5 is negative 8 square root of 5. Double that, and you get a negative 16 square root of 5. And then we have negative 2 square root of 5 times negative 2 square root of 5 is a positive 4 times 5, which is a plus 20, so that you can combine once again those constants, and your final result ends up being 36 minus 16 square root of 5. Our last example for the day is just the difference between two squares. So now the middle terms cancel out. So you're just looking at 5 times 5, which is 25. And then we have negative 2 square root of 3 times positive 2 square root of 3, which is the same as 2 times 2, which is 4, but it's negative, so negative 4. And the square root of 3 times the square root of 3 is 3. Negative 4 times 3 is a negative 12. And what's 25 minus 12? 13. And so that's your final result. And that's it. So if you want to try some additional exercises for section 8.4, highly, highly recommend that you check out these problems from pages 154 to 156 in our workbook. But other than that, that does complete our section 8.4. Your asynchronous is going to be 8.5 this Friday. And then just a reminder, you have your exam next week.